Going on a little field trip today. We're at NASA Goddard Space Flight Visitor Center. This is where we're all meeting. This is where the event starts to assemble. We're going to be working our way through different facilities, different science experiments and demos, and eventually make it to the Roman Space Telescope later on today to check that out. But I want to show you the visitor center first. So let's go on inside. I'll show you some of the cool things that you can check out. If you ever come up to the visitor center, remember they're only open certain days of the week. Let's check this out. What's over here? That looks like a James Webb Space Telescope model. That is, yes, look at that. So that's super, super cool. This is 1/20th scale. So you imagine the official one is much, much larger than that. A beautiful model that they have here. You can learn all about it too, all of the different telescopes, and of course, this is the most powerful one ever built. We're going to be learning about one today, but this is just one of the things that you can see inside. Look at the primary mirror. So this is there are 18 of these. They'll work together as one 6.5 meter primary mirror. So that's how it works. So when you see on the model right here, you see one of these, but then it's actually right here. So that's just one of the many. So you can kind of get an idea on how the JWST works. Again, this is in that L2 orbit, so this is far away from Earth. This isn't orbiting the Earth like Hubble is. This launched on Christmas Day, if you remember, in 2021. All right, everyone over there kind of getting ready to go. Let's see. Let's check this out. Samples of ice cores. Oh, I might have to do that later on. Put my face in there. Ice cores. Learn about those. How satellites see, how they work. Very useful tool for us for weather forecasting. Earth observing satellites. Look at all of them. There's tons. We mostly just focus on the GOES satellite, and that's a geostationary one. I will use Landsat once in a while. Here's ISS. So a bunch of different satellites. I've used and sprinkled with some of these. A lot of these are for research, not so much for weather forecasting, but I will be I'll be using those, and we'll have to take another look. Maybe we can get those on the show on a future time. Look at that. This is supercomputers on the case. So we're looking at the different parts of the atmosphere. This is using, or looking at dust, sea, salt, black carbon, and organic carbon, and sulfates, all circulating through the atmosphere. You can see how a storm, coastal storm, looks like got pushed off by a front right there. I'm not sure on the date, but we could probably reverse engineer if we wanted to and figure out when that happened. So there's a lot of different things inside this visitor center. Highly recommend coming out and check it out. Some cool things and models in the middle too. You can see how all of these different covers. Pistol grip tool, the main tool for all 5 Hubble service missions. So it's like a cordless screwdriver. Look at that. Huh. How to keep things lubricated so they wouldn't get stripped. So basically a grease gun, but a little bit more fancy than that. Have a model of the shuttle right here. That's pretty. With Hubble inside, of course. That was a big deal then. And then International Space Station right here. Early concept of Orion, obviously we see how that spacecraft has changed, where there's 4 long rectangular solar panels, not just 2 circular ones. It looks closer to that configuration, if you remember. I don't know what scale this is. Let's see. Oh, scale 1/100. All right. That's a lot of things that you can see inside here, the visitor center. Oh, I didn't even look up. Got to look up. Super, super cool. Hubble right there, a scale. I don't know what size it is. Let's see. Doesn't say. But anyway, that's some of the things that you can see inside the visitor center. There's a gift shop over there. There's some cool things you can get there too. So if you're ever up in this area, Greenbelt, Maryland area, going through DC, come on by through here. This is pretty fun. There's a lot more things that we need to see inside of Goddard. We're heading there next. Welcome back to Beyond the Forecast. You can see we're doing a special edition episode because we're at NASA Goddard Space Flight Center. Fun to see the visitor center. Even more fun to see this topic here, the Dragonfly mission. Now, this is a spacecraft that's headed towards Titan, the second largest moon in our solar system. It's so large it has its own atmosphere. Its atmosphere is made of mainly nitrogen, around 98%, 98.4% nitrogen, 1.4% methane, and 0.2% hydrogen. Now, compared to Ganymede, it's a little bit smaller than that, but Titan is larger than the planet Mercury. It's that big of a body, of an object. It's also larger than our moon as well. So it's a very large object that orbits Saturn. A great quote here by planetary scientists at Johns Hopkins Applied Physics Laboratory and the Dragonfly principal investigator, ZB Turtle. Dragonfly isn't a mission to detect life, it's a mission to investigate the chemistry that came before biology here on Earth. Now, what we're going to do here in this next segment is we're going to be talking to Dr. Charles Malespin, who is the Gas Processing System lead at NASA Goddard, and we're going to be talking about the science and the mass spectrometer that he's going to go over on board Dragonfly that's at NASA Goddard.
On this side is where the carousel and all the cups are and all the cold cryogenic section, but on this side is where the warm side in the lander will be with the actual mass spectrometer and the gas chromatography system that does the analysis. So this group has built mass spectrometers for a variety of different missions. We have built sample analysis and Mars instrument, which is on the Curiosity rover. We built the MOMA instrument, which is going on the ExoMars rover, launching from, it's an ESA mission launching in 2028. And then we have now building DRAMS for the Dragonfly mission. So we have a lot of experience building these suites of mass spectrometers and these instruments that go to a variety of different planetary targets. And we leverage a lot of that to build and cater these to the specific target that we're going to. So you can't just take SAM from Mars and drop it on Titan and expect it to work. So they're very different conditions, and they're very different missions of what you're looking for and trying to measure. So this is an ion trap mass spectrometer, whereas SAM on Curiosity, you can see some of the hardware over there, was a quadrupole. But really, these are very, very complicated instruments that process samples to try to detect both the organic content, but also the bulk abundances of what the composition of that material is. So Dragonfly will be a quadcopter, like the size of a small SUV. So we sit, this whole instrument, this is a 1-to-1 scale model, we sit up here in the front of the lander. So we have the cockpit view, we call it the attic, so we take up this whole front part here. The quadcopter will be landing on the surface, and there's a drill on the side, on the skid, and that's how we acquire samples. So we'll drill into the ice and then pneumatically transfer into one of the cups here on the carousel. So depending on which cup we use, we can either heat the sample up with an oven. So we heat it up to a few hundred degrees centigrade, and then as the sample heats up, it starts evolving and releasing gases that get sent to the mass spectrometer. Or we can do another mode that's called laser desorption, where we zap it with a laser, and you ionize the sample, and then that gas gets transferred to the mass spectrometer, and we can do analysis with that. So as we do this, the lander will be flying many kilometers each flight, landing at different sites, and we'll be exploring an area called Selk Crater. We believe that it was an old crater impact at one point, and there's a huge, vast, rich organic dune field that we're going to be trying to explore as well. This instrument will be the main instrument that does most of the analyses, but there's a bunch of other instruments that have the capability to provide context for us so we can help interpret the samples that we're analyzing and the stratigraphic and geologic context of what's around it as well. It's minus 180 degrees Celsius on the surface, so everything is just frozen completely solid, right? So some parts will have more water ice than others. We have a neutron experiment that can measure down and penetrate and determine the water content. We don't want to take too water-rich samples because that's not great for the mass spectrometer. So we're going to be looking at that, and then we anticipate that it's some bedrock with some ice slush mixed into it. So it'll be a combination, but that's the fun part about this mission is we don't know a priori really what we're going to see everywhere that we go. So we're excited to see what Titan offers us.
Yeah.
Question.
What's the duration of the prime mission?
2 years.
2 years.
Yes, but I had mentioned this before. So as you've seen with Curiosity, we've been on the surface since 2012. So we over-engineer these missions, and they can last much longer. Like Curiosity, it'll be an MMRTG, so it'll be nuclear powered. Small little marshmallows of plutonium that decay and generate heat. So we're not solar powered. Saturn is way too far for that anyway. So the energy source could last 10, 12 years or so, depending on how the battery's charged. But hopefully we'll be going much longer than the 2 years.
What's your comment on the weather on Titan and wind? Is that going to be an issue for flights? Do we know much about that?
We do. So Titan is pretty calm wind and calm weather. It is almost always minus 180 degrees Celsius, so there's no seasons. There is some electrostatic charging, and so there's been thoughts of methane lightning happening, but that seems to be a super rare occurrence. So while again, it's one of those things where we think we understand, but one of the reasons why we're going is to better understand these things. So it'll be interesting flying for the first time, going through to see what the atmospheric turbulence is like, both at the surface and then if we go up, a couple hundred meters to fly, if there's any differences in that. So that's going to be exciting. And we have very high resolution cameras that'll be flying and taking videos while we're going through this. So this is going to be wild videos to see for the public when we get them back.
Will there be a microphone on board too?
Yes, and we also have, pressure, temperature, all that stuff. So.
Nice.
For the nominal 2-year mission, how many flights do you anticipate doing?
That's a good question. So it'll be discovery driven. We could fly, a few kilometers. The way that it's going to work, it's called grasshopper modeling, I think is what it is. So we'll fly out, we'll scout a spot, and then you'll fly back to where you originally were so that you can scout a safe landing spot for the next time. We'll drill at that location, we'll do an analysis, and then we'll fly to the place that we scouted, we'll do a drill location there, you'll go out, you'll look for the next one, you'll come back. So we anticipate landing at a spot about 20 kilometers from our primary end target in Selt Crater. So if we imagine 2 kilometers per flight, that's about 10 flights or so. It'll probably take a couple weeks between each one just because of the way Titan rotates, and when it goes behind Saturn, we can't talk to it for, a week or two. So all that in the next 2 years that we have, probably about 10 to 20 flights, I would guess.
Was there any thought in the planning of this to send a communications probe with it to augment the ability to communicate back with Earth?
There was, concepts get thrown around all the time, and then you have to start descoping things when they start adding zeros to your price tag. But we could find a way with this large high-gain antenna, we can do direct to Earth. The bandwidth is very slow, so, you're like AOL dial-up back in the day with that kind of stuff, but it was enough for us to get the telemetry that we needed, and the added cost of adding an orbiter was just not worth it at that point. So, yes.
Yeah, for DRAMS, I know you've got 40 cups, but you only have 40 cups. And I'm curious, how much material does each cup hold? Do you hope to get into it? How long does each test take for each of those? And can you do multiple per site, or do you have to actually fly to a different site to the next?
Right. So the cups are, if you know anything about Curiosity, they're a little bit different from SAM in the sense that on SAM and Curiosity, the rover portions and drops it directly into the SAM cups. Here, the cup puts itself into the flow path of the pneumatic tube, so it self-meters itself and fills essentially to the top of the cup, right? So once that cup is full, it's full. Whereas on Curiosity, we put portions in, and you could put 12 portions into a cup. So we usually only take 2 or 3 portions. So you can use one cup multiple times. Here, these cups are one and done because they're going to get filled up, and then once you heat it up, that sample is going to stay in there. That ash is just going to stay in there. So there are tricks that we can use to try to reuse cups, but we haven't gotten to that point because we feel that 40 would be plenty for the prime mission. Each analysis will take between 5 and 6 hours, depending on the mode. So gas chromatography is the one where we heat the sample up and send it to a subsystem over here provided by our French colleagues at CNES. That's about a 6-hour experiment. The laser desorption experiment is about 5 hours. And there's just differences in how we heat up the system and how long things take to get to operational temperatures. Because it's so cold, it takes forever to heat everything up. So.
And is that the only instrument that can be working at that time when you're doing those tests? Is it that kind of power?
It's pretty power hungry. There can be like background measurements of just the smaller passive instruments, but nothing, it's not like we're flying and doing DRAMS at the same time. So it's very analogous to how SAM works, where the rover just goes to sleep, SAM does its thing, the rover wakes up, sends the data back. The lander will go to sleep, DRAMS will do its thing, wake up, and then send the data back to us. It'll probably use 20 to 30% of the batteries before it has to recharge.
Maybe have time to read one question like to dump on our bus and the next portion of our trip.
Sorry, I missed your first walk and talk. Can you do just a quick 30-second tour around the model?
Sure. So this is the carousel over here that has all the cups. This is the view you guys saw in the clean room. Over here on this side, this big giant gold box, this is the main electronics box. So this is the electronics box that has all the slices that control all the instruments. So it provides all the heater, gets all the power, does everything like that. On the inside here, you can't see it from here, but this is the main, this is the heart of the instrument. This is where the mass spectrometer lives. This support wall here is just for structure. And then on this side of the wall is the gas chromatography subsystem that was provided to us by our French colleagues at CADES.
Welcome back to Beyond the Forecast. So we saw that first kind of overview of the mass spectrometer. It's kind of complex, but I hope that made some sense to you. Just kind of as a note too, there's a huge group of media that we were kind of touring around different areas. So it was hard to kind of get close and to do a lot of one-on-one questions, but he got some information, some phenomenal questions and answers during that segment. And we're not done yet. Now we're going to be talking to Dr. Shannon MacKenzie and also Dr. Melissa Trainer. Both of these are Dragonfly's deputy project scientists or deputy principal investigators, and they're going to give us more insight on that sample collection, and we're also going to take a quick little look inside the clean room on where this part of this is being assembled. Now, just as a reminder, Dragonfly is launching in 2028 and arriving in 2034. So it takes a long time to get there. It's a long mission just to get to Titan, but once that starts, that's when the collections of the samples will begin. Let's check this out.
Main thing that you see with that view is our sample carousel that has a lot of spikes on top. They're called like the bed of nails or the porcupine. That's actually a thermal feature. We want to keep the samples that go into that carousel as cold as possible. So what was the Fahrenheit again? The surface of Titan is minus 300 Fahrenheit. Yes. Very cold. And we take the surface samples and we don't want to heat them up too fast. We want to keep them as cold as we can, even while they're in our carousel and moving around. And after you guys are done here, you'll get to go see the model and get closer and touch the model of what that instrument is, ask more detailed questions about components. But we use those spikes, actually cold air from Titan is flown in through the side of the lander and over it like a chimney effect. And it helps transfer heat to keep the sample carousel region as cold as possible, kind of in a passive way. So that's what you're seeing. Trying to think. Shannon, I'm sorry, Dan.
That's on the back. Yeah. My name is Shannon MacKenzie. I'm also a planetary scientist. I'm the deputy project scientist on Dragonfly. So have you guys heard about Dragonfly yet today?
Yes.
So you already know that we're going to Titan, Saturn's largest moon, because it's one of the best places to go and trying to understand what kind of chemistry happened before all the chemistry happened for biology.
What are your thoughts on what the atmosphere is made of?
Okay, so the atmosphere we actually know pretty well from the Cassini-Huygens mission. And so the combination of flyby-based measurements from the Cassini orbiter and also the Huygens probe, which was dropped through the atmosphere of Titan, actually carried a mass spectrometer as well that we actually have the flight model, the engineering model upstairs. And so from that, we're able to get the bulk composition of the atmosphere, the combination of all those measurements. So we know it's mostly nitrogen. The only other place in the solar system that's mostly nitrogen besides Earth, which is cool. A few percent methane, and then there's some hydrogen. There's some other trace organic compounds that are products of, we think, the methane photolysis. There's some acetylene, some ethane, and then you get the bigger the molecule gets, the less and less of it there is. But ultimately, because the size of the molecules that are formed with that atmospheric chemistry and then the temperatures, the really cold temperatures, it condenses into solids. And then that's what's kind of falling.
How dense would the atmosphere be too?
So the atmosphere, the surface pressure is about 1.5 times that of Earth, but it's because it's very cold, you end up with an atmosphere that's about 4 times denser than Earth's, what we're in right now, Earth's atmosphere. And that's part of how we're able to fly.
Yep.
And when you're looking at scouting to different places, once Dragonfly lands, how quickly can you shift into sample collection and science analysis with the instruments?
That's a great question. Shannon, do you want to take that one?
Yeah, so we have the benefit of working on Titan time. So each Titan day, the time it takes for the sun to rise and set and come back around is 16 Earth days. So we're only in communication with the Earth whenever the sun is in the sky, because there's no orbiting elements around Titan. So Dragonfly is doing most of its science during that waking period during the Titan day. So over the course of 8 Earth days, we would wake up, do a flight on Titan's about 9 o'clock local solar time, arrive at our next site. The flights take about 20 minutes. And then we actually have to do nothing for a little bit. We'll take some initial pictures, but then we have to hibernate and recharge our battery. A couple Titan hours later, so a few Earth days later, we'll start doing some of the measurements that we need to do to inform whether or not we should run DRAMS. DRAMS is a very precious instrument. Each of those cups is going to be something we think really carefully about before we use one. So we have other instruments that we want to take data with first before we decide to run DRAMS. And that would probably be on the next Titan day. So, 16 days later.
And how many cups are on DRAMS?
There's 40 sample cups. Some of them can be reused, but some of them cannot. And there we have 2 different modes that we use to analyze samples. And so there's different cups for different modes.
Do you get a full charge out of the RTG? How long does it take to?
That is a moving number. So the way that we ultimately charge our battery is through the radioactive decay of plutonium. So that becomes less efficient with time. And that is only a few % of the power that we would need at any given time, which is why we run everything off of our 300-pound battery. So you can imagine it takes some amount of time to charge that. And it also depends to what state of charge we need to be when we are doing different measurements. Before we fly, before we run DRAMS, we want to be topped off.
Okay.
Yeah. So we have that, just a couple.
So it's not necessary.
Yeah, so anyone who hasn't gotten a chance.
So it's not necessary. So you're not necessarily recharging every cycle. You're just recharging based on what the activity is going to be.
We're recharging a lot of the time. So we have these periods of awake where the lander's awake for anywhere from like 4 to 10 hours and Earth hours, and then we go back to sleep. And that is because we are always charging that bar.
Okay, so you're always off.
Yeah. We have the advantage of that nighttime to do a big bulk of charging.
Right.
Yeah.
What are the planetary protection protocols for this compared to, say, a Mars mission?
So Titan actually is in a different planetary protection category than some of the areas on Mars that we've gone to, mostly because of 2 things: how cold it is and that there's not surface liquids, and also how thick the ice is. And so the team, in concert with NASA, the Planetary Protection Office, did an assessment, and we are really under stringent planetary protection. We're really a chemistry mission, not a life detection mission. And so what we're much more concerned about and spend a lot of our time on is contamination control. So that's a really big deal. We don't want to go all the way to Titan just to measure, my fingerprint. That would be no good. So we spend a lot of time worrying about every single organic molecule that could be in the system, because that's what we're so focused on measuring.
Well, thank you to everyone at NASA Goddard Space Flight Center for all of that information regarding Dragonfly. Remember, Dragonfly launches in 2028, and it arrives in 2034 to Titan, the 2nd largest moon in our solar system, right after Ganymede, and much larger than our moon that orbits the Earth. So this is going to be a really exciting mission, especially how thick that lower atmosphere is to help them fly. Fascinating. We're going to have more on that as that mission comes closer. Maybe we'll go back up to Goddard and see if we can learn a little bit more too. But thanks again for watching this episode of Beyond the Forecast. We'll see you next time.